Develop some ongoing theories, I would say. So yeah. I don't know about a whole new one, but certainly I've developed some new maths to be able to handle how to model particles and accelerate the electrons in accelerators. So I'm quite excited by that. I've got a PhD student starting in a few months who will be looking at that. So yes.
And we were talking about time dilation and this morning, but actually you're actually cloaking time, is that right?
Well, proposing methods to cloak time, me and some of my colleagues, and we are some other experimental people have actually managed to make it work, which is quite exciting. Yes.
Brilliant. And how much time have you lost in your experiment?
I think they can do a couple of picoseconds.
Where do they go?
They're cloaked. They exist only in their own universe.
Great, brilliant. All right. Well, that could be for a future topic. So thank you very much, Jonathan, for joining us here. And you're going to do some stuff on general relativity. So over to you, and I'll take my mic off. Questions in the chat, everybody. Over to Jonathan.
Okay, hello and welcome. So this talk is going to have 4 bits. It's going to be a short lecture on special relativity, even shorter than I was intending to do before, because I realized that some of the things I was going to say have actually been said, so that's good. There's then going to be the workshop on special relativity, where we will be covering the items in the workshop handout, okay, which hopefully you've all downloaded and printed out, or at least printed out the minimum bit, and we will go through those questions. I'll be here, we'll all be here to give you help and so on. There'll then be a short break, and there'll then be a short lecture on general relativity, and then the workshop on general relativity, where hopefully you will all have an orange and a bagel in which to draw ideas from general relativity, because one of the thrusts of this, the idea of these 2 talks is all around trying to see things from a geometric and pictorial way. So the idea is that we'll be seeing what general relativity looks like in a more pictorial way. So you see here there are 2 chairs, and the idea being that some of the ideas from general relativity have been used in day-to-day work on actual experiments, where we have used them to make things disappear. So that's the thrust of the last bit of the second lecture. So you've seen that slide, well, not that slide, but you've seen the same thing. This is all coming to the concept of time dilation. Okay, how do we understand time dilation? Well, the easiest way to understand time dilation is in terms of space-time diagrams. Okay, so that's the main thing I'll be introducing in this course, in this short lecture. But before we get on to time diagrams, I just want to give my personal take on how you can have this time dilation where the twin paradox is not a twin paradox. Okay, so just moving my mouse here, and I've got a piece of paper here. Now I'm going to focus, with any luck, yes, brilliant. You can see that. Can everyone see that? I take that as a yes. Right, so my daughter has kindly provided me with 2 creatures here. Okay, and the one thing, of course, I don't have is a ruler. So, I've got two directions of travel here. Okay, and the blue one is going to be traveling in a straight line along here, and the green, so I don't know what these are. Okay, maybe in the chat you can suggest what these two creatures actually are. Okay, now both of these take a number of steps. Now I normally do this when we're in normal circumstances and we're not on COVID. I actually get a couple of students to come up and do this experiment. Okay, so this one moves forward, let's say 3 steps. So 1, 2, 3. Okay, and it's there. And this one moves forward 3 steps. 1, 2, 3. And I think I've got the positions right. Okay, which one is in front? Okay, so how would you judge if you're in front of someone or not? Well, let's call them guinea pigs. Brilliant. That's brilliant. Thank you, Kenneth. So if we were in a car and we were trying to judge whether we were in front of the other, we would look outside the window and we would look perpendicular to the direction of motion we were going. So this one, the blue one, looks out the window and you see it obviously thinks it is in front. But the orange one, she looks outside the window and she also thinks she's in front. So both guinea pigs think they are in front of the other. Congratulations, Kenneth. So, is there a contradiction? Well, only if you consider that being in front should be a universal concept, not a personal concept depending on your frame of reference. And this is the same concept as we have in special relativity. If you abandon the notion that time is something that's universal, that everyone has the same concept of time, but you would say, okay, my time is what's measured by me, depending on my motion, then there's no contradiction at all. Okay, so that is, if you like, the answer to the twin paradox. Of course, David gave an example of somebody flying off to a nearby star and then coming back again and answering and posing the question, which one was younger? Well, of course, in order to be able to do that, one of these two guinea pigs has to turn around and go on the other path. So we'll say that this yellow one here, sorry, the orange one, is going to go along a path like that. Okay, now let's measure it out. So we've got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and now move my camera a bit. Okay, you can see that the blue one is in front of the orange one. Okay, now what was it that made the blue one go in front? What broke the symmetry? What made it the blue one and not the orange one? Okay, does someone want to type something into chat? No one yet? Well, what did the orange one do here? Okay, the orange one precisely had to turn round and change direction. So it's that breaks the symmetry. Okay, now if we go to the example of flying off to Alpha Centauri and coming back again, okay, again it will be the orange one flies off to Alpha Centauri. So I have to draw another star there. Okay, and then comes back again. again, what happened here? Well, the orange guinea pig was moving in that direction and had to turn around and came back again. Okay, so the orange one had to accelerate, the blue one didn't accelerate. So it would be the orange one, which in this case is younger. Okay, you've got to now question why when it was traveling and we were just turning the steering wheel, is it longer? But when we're accelerating in time, it's shorter in the sense of less time has passed. Well, that is simply due to the difference between space and time.
Jonathan, can I ask a question, if you don't mind, people?
Please.
Asking. So where does length contraction come into this?
Okay. Well, length contraction, there is on the worksheet a rather long and quite difficult question. I think it's the last question, exercise 5, where the space-time diagrams of everything is presented, and hopefully, if you understand, if you go through the questions, that will all make sense. But as a quick analogy, as I just showed Phil beforehand, okay, I've got up here, I've got 2 pens, okay. Which one is the longer pen? Well, according to the blue pen, it is the longer pen, and according to the green pen, it is the longer pen. So it's the same kind of idea, that it depends on your frame of reference, okay? But that is even more precisely made when you do the full space-time diagram, because the actual concept of how long something is a little bit complicated, okay? It's a bit more complicated than how than time intervals are. Okay, but so how can we do all this stuff with space-time diagrams if we don't know what a space-time diagram is? So the rest of this short seminar will be on space-time diagrams. Let's bring it back again. Oh, I keep disappearing here. Right, stop it. Okay, so how do we make a space-time diagram? Well, space-time diagram, space and time are on the same footing, okay, in special relativity and in general relativity. So we consider Bob. He leaves school, he leaves his home, he walks 4 kilometers to school along a straight road. One day he leaves his home at 8:30, walks to school, which takes an hour as he's late, and stays at school until 12 o'clock, and then walks home and stays at home because he's very lazy. Okay, here is his space-time diagram. Okay, so the first thing you notice is that Bob is no longer a point. Bob is a line. It's called his world line. Okay, he starts off at home. He walks to school. I hope you can see this. I'll just highlight little bits of it. Okay, he then stays at home for a couple of hours, and he then walks back to he stays at school for a couple of hours there, and he then walks back along this red line here, and then he stays at home. Okay, so this is the world line of Bob. Now, as has been noted before, light travels very quickly. It travels 300,000 somethings per, I think you write it in furlongs per milliliter or something like that. Okay, but a far more useful for special relativity, a far more useful time and distance is time in seconds. Okay, and they go up here, and traditionally we always put the time in along the vertical axis and distance along the horizontal axis. And the distance here you'll see is in light seconds, okay, which actually means that the distance from here to here is a long way. Okay, that's 300,000 kilometers, if I'm right. Okay, but of course units, you can choose whichever units you like. Now light travels along at 1 light second per second. Okay, so it's traveling along this yellow path, oh, that doesn't highlight it very well, this yellow path here. Okay, that's my light path, and that's at 45 degrees. Any permitted path, so that's any path of something with mass, okay, will travel slower than the speed of light. That's one of the conclusions of the talk by David. If you remember that gamma factor, as you approach the speed of light, your gamma factor got larger and larger and actually went off to infinity. So there's no way you can travel faster than the speed of light. Okay. There's also forbidden paths. Okay, and that is things moving faster than the speed of light. Okay, so this path here is forbidden. Okay, now you will have hopefully printed out a space-time ruler now. So unlike a normal ruler, okay, there's two ways of having a normal ruler. Of course, I don't have a normal ruler. I should have bought one before this seminar. But if I was going to make a normal ruler on a piece of paper, what I would do is I would start off with the point I measure from, that dot in the center there, and then I would draw a bunch of circles around it. Okay, and I'll call this 1, 2, and 3, like that. Okay, and that is a normal ruler. And my 1, 2, and 3 are upside down, aren't they? There you go. And if I want to measure the length of something, well, I just place it along this ruler, and I can see that my guinea pig is 2 whatever units that is. Okay, so that's an alternative to a normal ruler. Now, what you have here is a space-time ruler. Okay, and it's not quite, but it's quite similar to Pythagoras' theorem. So Pythagoras' theorem says that the length of something is the square root of x squared plus y squared. Okay, well, in a space-time ruler, the length of something is the square root of t squared minus x squared if it's in time. Okay, so these lengths, these blue lines here, they are length in time, and they go from what are we here, 0 to 4, and they're in seconds. Light is this green line, and that's always 0, and that's how long light ages by. So you get this amusing thing that we can see. One of the most distant things we can see, I think, is a supernova about 13 billion light years away. And if we could interrogate the light and ask them how long ago do you think that supernova happened, they would say, well, instantly. Okay, the light has not aged at all. Okay, and then so these are the green lines, and then you've got the red lines here. They are the space-like distances. Okay, and these are the curves with constant 6 here, and that's given by the square root of x squared minus t squared. So these are hyperbole. Okay, and using this space-time ruler, you can place this on your on the space-time diagram for Alfred and Beatrix and decide which one is the older. So that's I think that's question. Hold on a minute. I'll just have a look at my questions. Yeah, so that's exercise 2. There you go. So you can use your ruler, hopefully, to have a look at that. Okay. Now, on a space-time diagram, okay, here we've got observer 1 going up vertically. Observer 2 is moving along a different curve, because observer 2 here, this is a different observer, and that's moving roughly 2 light seconds every, what's that, about every 6 seconds. So it's moving at about a third of the speed of light, and that would have this black line here. Okay, so that's the easy one to understand. That's its world line. Carrying with it is an axis, the space axis. Okay, and normally, if I rotate an axis, I just rotate them like that. Okay, because I'm preserving, if you like, x squared plus y squared. I'm in standard Pythagoras. I'm preserving angles. Well, in this case, I want to preserve this space-time angle, and so as a result, the axis moves so that it is just a reflection of this axis about this light line. Okay, and as this becomes more light-like, so does this become more light-like, and that corresponds to moving faster and faster. And what do these blue lines actually mean? Well, this blue 2 here, if I, from every direction and every speed I travel from this point here, after 2 seconds, so long as I don't accelerate, after 2 seconds, I will arrive along this blue curve. Okay, so this blue curve is the 2 seconds for all inertial frames from this point here. Okay, so I hope, I can't look at your faces. I'm expecting you all to be smiling and nodding in approval, but I hope that makes some sense. Okay, if I take an event in space and time, so I've chosen a particular event here that's obviously important for me because that is the moment of my birth, that's this point here. And that divides space and time into 4 separate places. Okay, the most important for me is this region here, and they're all the moments of my life, all the events in the future of my birth. Okay, so my entire life must take place inside this region here. Okay, this and that would be the future of this point. This point, this back thing here, they're all the points that led up to my birth. Okay, so although I can't be quite sure where my great-great-grandparents met each other, I know that it took place in this region, okay, because that directly influenced my birth. Likewise, the supernova, actually, no, that's not true. If I observed a supernova at my, if this was now, okay, and I was looking at that supernova 13 billion years ago, that would have taken place here, okay, somewhere along this, inside this region. And then there's this rather confusing dark blue line, and that's all the events that neither influence my birth or can be influenced by my birth, okay? This is a sort of other. Of course, space and time have 4 dimensions. We have 3 dimensions of space, and we add time, so we end up with 4-dimensional space-time. I can only draw 3 dimensions, or represent 3 dimensions on a piece of paper, like normal. And you see here, the future is a cone, the past is a cone, and this elsewhere, well, that actually connects together. So when I said back here that there were these 2 regions are distinct, when I go to 3 dimensions or 4 dimensions, they actually connect together. So there's a lot more elsewhere than there is past and the future in that sense. Okay. Of course, I can't draw a 4-dimensional blackboard. Unfortunately, I have one that I use to demonstrate to the kids, but due to the coronavirus, I'm limited to just this 2-dimensional screen. And that, in 25 minutes is about right. is the end of that lecture. I will go on after the break to talk about gravity and the space-time cloaking, which is also related to that. And hopefully people can now start working on these worksheets. Okay, I don't honestly expect many people to get to the end of it all in 30, 25, 30 minutes. But see how far we get. And there is, I have typed up now all the answers. Okay, so they will become available to you when after this session.
So,
so Tim is starting exercise 2. Well done.
yes, go on. Well done, David. Right, I've unmuted you, David. You can talk us through. It might be better the other way around. That's better. Yeah, we can do it there. That's good. I can see that. There we are.
Okay, so we've got there point A, O to A. So putting the axes of the space-time ruler on O there. A lies on the 3-second line. So I've got point A as being time-like, and it's going to be in the future of O, and it's 3 seconds away. Is that the correct way of reading it, Jonathan?
Yeah, that's absolutely correct. Yes.
B is space-like. Again, it's O to B, so I've got the origin of the space-time ruler on the origin here, but B is now on the 3 light second mark.
And can I emphasize what is important there is there's no concept of whether B lies in the past or the future of the origin. So David's got that correct of leaving that bit blank. Thank you.
Okay. OC is on the light line. So is it? Are we right that this is in the past?
Yes, that's in the past.
Yeah, but of no length.
Mm-hmm.
Because it's sort of effectively in line with the origin. And then for AB, I need to move my space-time diagram so that the origin is now on A. Trying to keep an eye on the screen and the diagram. And point B is now, well, I've got it just short of 9 light seconds away from A.
Yeah, I think it's about 8.6 if you use the formula.
Okay. And B to C, so now I've got to put the origin of my ruler on B. And I've got to look where C is. So C will be in the past of B, and it's about 5.5 seconds earlier.
Yep.
Yep. And A to C, so I'm taking my origin back to point A, and point C is in the past of A at about 4 seconds.
Mm-hmm. It gets a bit difficult to see at that point, yes.
Yeah.
Brilliant, thank you very much.
That's great, David. That really shows question 1. So are you going to now move on to question 2?
Do you want me to do that in the same way?
Yes, please.
Okay, so I think on this one, because Beatrix, well, let's do Alfred first. So if we put the origin of the space-time ruler at the start there, and we follow Alfred's world line up to the end of the journey, and that comes to, I'm not sure you can see the scale through the paper there, but that's just 8 and a bit years at this point just here. 8 and a bit years for Alfred up there.
Okay,
now,
David,
yeah.
I just want to stop you because some people might have just got the hang of this.
Oh, okay.
And I just give you just leave it for a minute for people to work on the next on part
Okay, that's
B.
fine.
Just give it a minute and let's see if we can. Okay, David, would you like to show how you do part B?
Okay. So just to recap on Alfred then, if I put the origin of the space-time ruler at the start of the journey and simply follow Alfred's world line straight up to the end of the journey to point E, then I think we are on 8 and a bit years. Let's call that 8 1/4 years, just looking at that. Now, I think if I understand it correctly, the thing with Beatrix is because she has changed direction to turn around and come back, we've got to do her journey in 2 halves. So I think for the first part of the journey, the origin of the space-time ruler is in the correct place. And I think Beatrix's outward journey to here, which lands on the 3-second line. So I think she takes 3 seconds to go on her outward journey. It's quite a fast journey, so by the end of that journey, she's now a certain distance away from the origin, and she's taking 3 seconds to get there. For her return journey, I think you've then got to put the origin of the space-time ruler at the bend, as it were, and treat that as a separate journey, and see where the end of the journey is in relation to this origin. So she is now, the return journey from there is another 3 seconds to get back. So in total, she has been away for, sorry, I kept saying seconds, it should be years. She's been away now for a total of 6 years, whereas Alfred perceived it to be about 8 1/4 years. I say perceived, perhaps I should say it was 8 1/4 years for Alfred, and it was 6 years for Beatrix.
And actually, that shows how there's a change of direction, because when you move the origin, the line goes onto the opposite direction than the original direction. If you get my drift.
Yes.
This is Jonathan. This is a really good representation of doing, showing this. So well done for that.
Thank you.
So there's still part C and part D, David, if you want to carry on.
Right. Okay, so C was to do the alternative world lines, wasn't it? So I guess you've already seen the answer to those, because those are on this sheet here. So the alternative grey lines here would be alternative world lines for Beatrix. So any combination of those would, or any one of those would do.
So David, why have you not drawn triangles going further and further to your right?
Yeah, so well, that's actually on your sheet, I think, Jonathan, actually.
Yes.
There, but yes. So one of those grey triangles, any one of those would be the answer. Okay.
And then
And
how do
D,
these times compare to that to Alfred?
well, Alfred's will be the same, won't it? Which you could use your
You mean
space-time
Beatrix?
ruler.
Yeah. But the others
I guess you could. Yeah, the others will be a shorter length of time because they are faster and closer to the speed of light.
Yes. Yeah.
So therefore, I think the answer to the last question, what's the shortest world line you can draw? That would be 0, would it?
Yes, except you can't draw it, because
No.
then it's no longer a world line. So you can draw as close to 0 as you like, but never quite get there.
Brilliant. Well, I think Jonathan deserves a round of applause for this worksheet, and David, of course, for being able to present it. We've got a question for you, Jonathan.
Yep.
From Catherine. Please show an example of how to use the formula for the answers, please.
Okay, so I'm massively at the disadvantage of not having a ruler. However, what I do have are the points on of A, B, and C. So at the bottom of exercise 1, you see that there are the A, B, and C there. Okay.
Hang on, I'm making you presenter now.
Okay.
So
you don't. Yes.
you're presenting. Yeah.
Okay. Well, I'm not going to share my screen at this point anyway. What I'm going to do is I'm going to bend that down so that you can see my my workings, so to speak. Oh, that didn't work. Where am I? Sorry. Okay, can you see this piece of paper? Okay, and you see at the bottom of this piece of paper, which is of course, hold it like that. You see that the positions of A, B, and C are given in coordinates. So if we take the point OA, so we want this point here. Well, A is at -3, 4.2. Okay, so the first thing we see is that, if you like, the y coordinate is bigger than the x coordinate in modulus. Okay, so that tells us that it's time-like. So I'm going to square that. So we've got the time, tau, equals the square root of 4.2 squared minus -3 squared. Okay, and then I will now see if I can get a calculator up. There you go. We'll put that down here. We shall now share my calculator. Okay, and then I type in how do I do square root? Square root of 4.2 squared minus minus 3 squared. Et voila, something quite close to 3. Okay. Right. The important thing, of course, is when you're taking from A to B, of course, you've got to add the coordinates together or subtract one coordinate from the other, and so on. Okay, and if you want a time-like one, then you sorry, a space-like one, then you swap the x and y, no, the t and the x round, of course, because the one thing you want to avoid is having a complex or an imaginary answer.
Great. All right. Now then, I'm going to, because I know what the program is, and I know that what it's like for people to keep listening and stuff. So I'm going to enforce a break here. I'm going to suggest, Jonathan, that we don't do the other questions, because I know the ideas that you're going to share with us in the next session are really exciting. And for those people who are interested in carrying on with this worksheet, we'll find them out, and we could maybe in the future ask you to lead us through the answers. We could set up an hour session in the future sometime to finish the worksheet off. But right now, I'm going to say we're going to have a 10-minute break. So that means that at 14.
Can you see my screen? I'll take that as a yes.
Yeah.
Okay.
Can do.
Right. So special relativity does not include gravity. Okay. So how do we think about gravity? Well, Einstein liked to think of things in terms of simple thought experiments, and he observed that all free-falling, non-rotating cabins are equivalent for the performance of all physical experiments. That's his postulate. Okay, so if we think about a cabin floating in space here, okay, then I don't detect any gravity at my feet, okay, because I'm floating in space. And likewise, if I shine a beam of light from across the top, I don't see any, that beam of light goes in a straight line as I perceive it. Now, if I'm an accelerating cabin, okay, in space, okay, I will, when I stand on a pair of scales, I will detect some weight, okay? I will detect a reaction force, okay? And at the same time, if I send a beam of light, well, as the beam of light is traveling from left to right in this picture, of course, the cabin is moving, is accelerating, so the light will appear to bend, okay, or will bend. Now, what about the case in gravity? Well, the equivalent of floating in free space is that I'm free falling towards the ground, okay? I don't feel any weight, and the beam of light will travel in a straight line. It should be pointed out that this only happens for a brief moment in time before I hit the ground, and then the experiments would be somewhat different. Okay, if I'm on rest on the ground, well, then it's equivalent to this example of accelerating in space. So I detect gravity. I don't detect gravity. I detect my weight. Okay, because if I stand on a pair of scales, I see a reaction force, and light. Well, it has to bend because it's equivalent to this scenario. Okay, so we observe that light rays bend in a gravitational field. But the cabin must be sufficiently small, because if we look at a cabin that's so big that different particles fall in different directions, okay, as would happen here, then you can observe that. In fact, this is what we consider gravity to be. Okay, gravity is not the reaction force here, okay, because that can be removed simply by falling to the ground. Okay, and what's more, a reaction force might be due to simply accelerating. So what is gravity? Gravity is this, is looking at how nearby particles behave. Now, I actually set this as an example to do from when I interview candidates for Lancaster University, because it's quite a fun thing to run through and everyone seems to enjoy it. Okay, we imagine we're in a lift shaft and we're falling to Earth, but it's a big lift shaft. Okay, and we take these four particles. So I let go of two particles either side of me, and I let go of a particle above me and below me. Okay, and the two particles either side of me, well, it's easy to see that these, they all fall down, but the down is in a slightly different direction, because this is falling slightly inwards and this is falling, these are falling together like this. So when I subtract my velocity, because of course I'm falling with them, all I see is this residue acceleration inwards. Okay. What about the particles above and below? Well, the particle above, that's going to experience slightly less Newtonian gravity, if you like. It's further away. It's a 1/r² force. Okay, so that will accelerate slightly more outwards. Okay, relative to me, it will be as though it's being pulled upwards. Okay, and the one below is being pulled, relative to me, being pulled downwards. Okay, so I'm being two particles here are being pushed inwards, two particles out here are being pushed outwards. And then what the students really like is if this were to happen near a very, very intense gravitational field, of course, everything is being then squeezed inwards and pulled upwards. And it's a beautiful thing, phenomenon called spaghettification, because everything turns into spaghetti. Okay, now that is what we consider to be gravity, at least what I consider to be gravity, and this is due to curvature. Okay, and we're going to see this in the workshop, that if you have a curved things, then if you have a curved surface, then some particles will appear to be pulled inwards, and some particles will be pulled outwards. Okay, it's also the reason why we have two tides a day. Okay, I think the A-level reason for this is well, the fact that you can do such a simple thing like this, and A-level students can understand it. I think this should be the reason that's explained in an A-level class. Okay, we're falling towards the moon. Of course, we're not falling towards the moon, but the moon's gravitational field is there. Okay, water, which is a lot more flexible than the Earth, okay, that gets pulled inwards like that and pushed outwards like that, and so you get a tide on the moon side and you get a tide on the opposite side. Okay, so there's a relationship between curvature and gravitational fields, and as we said before, starlight is bent by massive stars. And some of the you get some beautiful photos now with especially due to the Hubble telescope. Okay, this rather indeterminate light in the center, that's a mass halfway between us and a distant galaxy. And these four images here are all the same galaxy. We know they're all the same galaxy because we can observe the light coming from it, and the light has the same signal. So these four things are exactly the same galaxy, but they're being stretched in different ways. Okay, you get four images here because they are because the galaxy is not the most spherically symmetric. But if we take a black hole here in the center here, you get a ring. Okay, there, so you can imagine that's coming from this example here, but then you just rotate it. Okay, so this light purple dot here, that's rotated round and it becomes a circle in the most extreme case. Okay, but you see a lot of Einstein rings in the in images in the Hubble Space Telescope. Okay, so that describes how gravity affects light. Okay, but let's have a think about one of the most fascinating things about gravity, which is black holes. Okay, if you throw a ball into the air, it will return to Earth. However, if you throw it more than 11 kilometers a second, okay, it will leave Earth and never return. So this is called the escape velocity. Now, the escape velocity, there's a simple formula. I think you do this at A level, given by the square root of m over r, where m is the mass of the, when I say the mass of the object, the mass of the planet, okay, and r is its radius, okay. So the mass of a planet increases and the radius decreases, then the escape velocity increases. Okay, so for Jupiter, okay, Jupiter is bigger than the Earth, but it's an awful lot more massive. Okay, so the escape velocity there is 60 kilometers an hour. The Sun is even bigger than both, but it's even more massive than both. And so its escape velocity is 600 odd kilometers a second. Okay, now if we could squeeze the mass of the Earth down to 9 millimeters, then its escape velocity would be so large that not even light would occur and the Earth would become a black hole. Okay, how do we know there's black holes? Well, unfortunately, I've not got the image. I should have got the image of Sauron, or you know, the Eye of Sauron, which is a beautiful new image showing detection of black holes. We also have gravitational waves. So black holes have become, from a theoretical object, have become a now an experimental object. You know, we can observe them experimentally. And one of my favorites here is a supermassive black hole in the center of our galaxy. So it's called Sagittarius A because it's in the constellation of Sagittarius. We couldn't see it. Well, you can never see a black hole, but we could never see anything near the black hole before because it's all clouded in dust. But modern radio astronomy has got round that dust, and we can see all the objects that orbit the black hole. And I believe this S14, okay, when it's close to the black hole, it's so close that it's actually traveling at 10% of the speed of light. So as far as we know, that's the fastest macroscopic object that we know of. Okay, and if you model these orbits, okay, which we can do very accurately, we know that there is an object of a certain mass inside here. It's got to be that mass because that's dictated by these orbits. We also know the maximum size it can be because if it was any bigger, then things like S14 would collide into it. It should be pointed out these are all stars. Okay, then it's got to be a black hole. Either that or our whole understanding of physics is wrong. It could well be, okay, and a new version of physics will come along, which will be even more complicated and even more exciting, okay? But at the moment, our only statement of what it can be is a supermassive black hole. In fact, you know, 4.1 million solar masses, so that's big. Okay. If you have a black hole, well, as we know, as everyone knows, a black hole is surrounded by an event horizon. Okay, if a rocket comes along and doesn't cross the event horizon, it can then fly out to space. But if it does cross the event horizon, then it will fall inside. Okay, and it will inevitably go into the singularity and be crushed. Crashed and no longer exist. Okay, so if you're a sensible rocket, don't cross the event horizon. Now, one of the things I remember as a kid being told this by a friend of the family's, I've got a map of a black hole, and I thought this was fantastic. So everyone should see a map of a black hole. Okay. Again, this is stuff that is quite amenable, I think, to A-level students. Just the very concept that you, as we saw in the space-time diagram, you can only move more vertically than 45 degrees. Okay, so if I travel along this blue curve, okay, then I have to, then I will never cross the event horizon, and I will travel out to this point here. Okay, this is called the Penrose diagram. It's a very clever thing where they've squashed in infinity, but essentially this entire lifetime of this blue particle never crosses the black hole event horizon and lives a happy life. Okay, this red curve here, well, they might be happy, but they have crossed the event horizon, and they cannot do anything other than travel into this singularity. So you look at this singularity here, every point inside here, you have to hit the singularity. Now, this yellow curve, that's a spacelight curve. So you remember spacelight curves, these are traveling, well, not traveling, but they represent curves that would be traveling faster than the speed of light. No particle can travel along this curve. Now, with a bit of work, okay, typically somewhere around the level of a fourth year or first year master's student, we do it in our 4-year MPhys course, okay, you can see what Einstein's equations are, you can solve Einstein's equations, they're quite long, and when you solve Einstein's equations, out pops, if you like, as a solution to these equations, another universe, which is quite weird, okay? But that's okay, because you can't get to this other universe, because you can only get to this other universe by traveling faster than the speed of light. And of course, we know that nothing travels faster than the speed of light, so we're okay. So you cross everything is sort of as you would expect. You cross if you cross an event horizon, you must go and be crushed to the singularity. You can avoid, obviously, the event horizon. And there's another universe, but you can't get to it anyway. So that's fine. Okay. But this is a map of a non-rotating, uncharged black hole. Okay. Well, what happens if we have charge? Well, if we have charge, you can solve the equations, and suddenly you don't have one event horizon, but you have 2 event horizons. Okay, if you cross the first event horizon, you can then you have to, it should be pointed out, cross the second event horizon. There's no choice there. Then you're inside the black hole, but now the singularity here, you can avoid that singularity. So you can cross another event horizon and you can go into another universe. So when they say that black holes are, if you like, wormholes or doors to other universes, well, an uncharged black hole is not a door to another universe, but a charged black hole, well, if we believe the solutions to Einstein equations are doors to other universes. So the moral of this story is, if you're going to go into a black hole, make sure it's charged. What about a rotating black hole? And it should be pointed out that every black hole we know about, the model is, and the observations are, that they are rotating. So every black hole we believe is rotating. This is not surprising. If you think about how black holes are formed, they're formed by crushing rotating stars, and it's very difficult to get rid of angular momentum. So everything ends up rotating. Well, now the event horizon is the same. The singularity stops being a point; it starts becoming a ring. Okay. If you pass through or near that ring, you can get inside a kind of anti-gravity universe here. Okay, so this is a universe in which you can see the event horizon. You can see the ring singularity. Okay, so you could go in there. You still have other universes you can go in, and if you go near this ring, okay, and you go round the ring, you have to keep accelerating to go round the ring in a particular route. You actually enter what's known as an acausal region. This is a region that when you go all the way around the ring, you come back and you meet yourself. Okay, this is quite easy to show with a bit of maths. Okay, so there's an acausal ring, so you could play cards with yourself. Okay, which is quite bizarre. So I love this, these weirdnesses that go on. Okay, is this reality? Well, we believe that, well, first of all, these are black holes. I should say these are black holes that have existed forever. These are primordial black holes. Okay, we know that, well, the only mechanism we have for creating black holes is for the collapse of stars, and they don't have this kind of picture. So it's very unlikely that something like this exists. Okay, there's also the fact that near an intensely gravitational field, we would need a theory of quantum gravity. Okay, and we don't have a theory of quantum gravity. We have some candidates. Okay, we've got string theory, loop gravity, non-commutative geometry. We have some initial results, the famous Hawking radiation. Okay, but if there ever is going to be a theory of quantum gravity, okay, we need new minds, new young minds. Okay, that's what I tell the students when I present that to them. Hopefully, get them slightly excited. Okay, is there any practicality to all this? Well, it's beautiful mathematics. It's lovely bits of physics. Of course, we've already said how general relativity has to be programmed into your sat nav in order to make it accurate. But there's another application which I find particularly lovely. Okay, we've seen that light is bent by gravity. Okay, but gravity is not the only thing that bends light. Of course, if we stick a straw in a glass of water, we can bend light really easy. In fact, so much easier than this. This is really difficult. You need, black holes and stars to bend light using gravity. Here, we've just done it with a bit of water in a glass. Now, bending light, we propose, well, there's an idea that maybe if you can bend light, you can bend light round stuff. Okay, so you could use this as a way of shielding stuff. So this is an example of all the light rays emanating from this origin here. They come out and they're being bent round this object here and coming out like that. Okay, so this light orange region in here, that is completely shielded, and it doesn't matter what direction of ray it comes, it will always bend round and come out. Okay, now in principle, thinking about that's really easy. So why do you need gravity to do it? Well, the problem is, how do we work out what the refractive index, what's a permittivity or the refractive index that you would need to be able to create this cloaking? And what's more, how do we make sure that you don't get reflections? I mean, normally when you have a discontinuous jump in permittivity, of course, you get reflections as well, and that would at least indicate that you were doing something, and you don't want that. Okay, so how do we work out what the correct permittivity and permeability to get the correct refractive index needs to be, such that light that will always avoid this object? Well, what Pendry did quite recently is come up by using techniques of general relativity with a formula that told you how to bend light so that you could hide stuff. And so this is the idea of using concepts from general relativity. Okay. I'll skip that one. Okay. Now, the materials needed to bend light, okay, you've got to bend light in a weird way. You see, if we go back here, we see that some of the light is bent away from the normal. Now, that normally would mean that it's moving, if you like, faster than the speed of light in the vacuum, or you would need a refractive index of less than 1. And they don't exist in nature, but we can make them. We make them using a material, metamaterial, where we use a repeated structure of C's. These are little C's in there, and behind them are little I's. Okay, a clever metamaterial structure. And so long as the wavelength is sufficiently long, so here the wavelength would be 10 of these, about that sort of length. Okay, so long, sufficiently long, you don't see the wavelength doesn't see the individual structures. All it sees is the bulk. Okay, and by doing this homogenization, you can create whatever n you want. You can create it to be negative, so it bends around. You can even make, less than 1. You can even make it negative, so it does this rather odd shaped refraction. Okay, and what's more, people have built these. Okay, they've not built them for optics, unfortunately, at the moment, because the sizes are too small. You see, this is sort of millimeters in size. Okay, but they have built it for microwaves, a couple of centimeters. Okay, and they've built this, they've shone microwaves around it, and they've shown that it doesn't matter what you put inside the middle here. Okay, it will not affect the microwaves that come round it. Okay, they all will be bent round and come out. So, as I like to say, if you stick this in your microwave oven and you stick a chicken inside, we have now spent a lot of money to devise a way of not cooking your chicken, because all the microwaves would then bend round your chicken. Okay, and then finally, as we mentioned before, we can even do space-time cloaks where we've managed to hide some time as well. So that's a nice idea. This is work I'm working on at the moment with colleagues at Imperial. Okay, thank you very much for listening. I think there's going to be a short break where you dig up you go and get your oranges and your bagels. Okay, and then I don't know how Phil wants to do it, whether we have a session where I demonstrate, because these are things that I want you to see the answers, but I don't believe my instructions are sufficiently detailed enough that many people will be able to follow them. So it's no reflection on you not being able to do it. It's more reflection on me not being able to explain what I want people to do. Okay, so Phil, how do you want to do things now?
Well, so first of all, Jonathan, thanks again for that. Thank you for that talk and the other talk. There's some great ideas in there, and you're right. I think in fact, I'm really pleased that you've said that you'll take us through the next worksheet, because I didn't have a clue when I tried to do it. So, I think we should reconvene at let's say another 5 minutes.
Okay.
At 15:05, and Jonathan is going to take us through using the orange and the bagel and your black marker pen to the concepts of the of space-time, and we've got plenty of time, so we can take this quite slowly.
Okay, can I just do my advert for the Einstein packs?
Of course, yes. I mean, that has to start somewhere. So now's a good time as ever.
Go. The point. So if COVID had not come along, okay, our goal was to produce an Einstein pack that had some balls in it, some bits of hoops in it, drawn on. Other than these would be sent to school. It would also include a space-time ruler, a couple of space-time ruler printed on acetate, so that you can see through it, and then there'll be PDFs online, so that the teachers can print out all these worksheets and stuff. I mean, there might be paper copies in as well, but the idea is that they'll be able to print them out. and there'll also be short videos by myself, edited by Phil to make them all look professional, which will be similar to the lectures I've given today, and in addition, where I explain the answers to how to do the space-time work, the rulers, so the first part, and then go through the demonstration that I'm about to go through now. So depending on when we return to normal, if you add a few months and possibly a few months more, then you should be receiving in the post the Einstein pack. This will be sent out to, well, all the schools that Phil knows. Before then, hopefully you'll be sent out some balls and some acetates and so on, just for yourselves. So that's your bonus for signing up for this presentation. So I hope you all look forward to that. I certainly look forward to sending them out, getting them sent out. It should be pointed out that Andy Blake is doing all the heavy lifting for this. So thank Andy as well. Thank you.
I'm going to be asking for your addresses. So people who want to get this pack, they can send me their addresses. Actually, it was giving lots of information here. It might be an opportunity for you to open the feedback form, which I sent in an email last night.
Right. So since I'm still sharing the screen, the thing we want to bear in mind is this idea that gravity is curvature. This idea here. Okay. So we start with the flat plane, and we start with what is curvature? Okay. Now, curvature is what happens when I take an arrow and I transport it round in a loop. Okay, so of course, when I say an arrow, I mean a vector. Okay, so there's my vector, right? And I have a loop, which is a different color. Okay, and I transport it round whilst always keeping it parallel. Okay, and the thing you observe, okay, is that when I go all the way round, when I end up in the same space that I started, the arrow is pointing in the same direction. Okay,
Jonathan, it's not that clear really. Can you just move it back a bit? And now it's getting a lot of reflection.
You're getting reflection. Ah.
Yeah, well, it's not that clear. Have you got a heavier pen that you can use?
Yeah. I shall draw it again with a heavier pen. So thanks to the physics department. How's that?
Yeah, that's better. Perfect.
Okay, so I'm going to draw an arrow. I'm going to what's called parallelly transport it round. Okay, and the green arrows are all pointing in the same direction. Okay, so the piece of paper is flat. Okay, because that's what we mean by flat, is when you transport an arrow round or a vector round, it always ends up pointing in the same direction. We observe that even if it looks curved, okay, so I make a cone out of this, like that, it's still flat, okay, because my arrow is still pointing in the same direction. Let's do something which is not flat. Now, hopefully, you all have a piece of fruit, okay? I know some of you don't have fruit, okay? I'm sorry about that. Now, on your piece of fruit, I'm going to see if it works. I haven't actually tried it with a piece of fruit. I also don't have an orange, but I do have an apple. I'm afraid, well, I might peel this and then eat it afterwards. Okay. Take your a point which you're going to consider to be the north. Okay, there's my north N. Right. I'm then going to draw. I'm then going to go down to the equator. I'm going to consider that to be the North Pole. There's my equator. So I've drawn a line going down. I'm going to go across and then back up again. Okay. So that's the path I'm going to travel on. Okay. So that's the equator along there. Okay. I'm now going to take hopefully a different color. Okay. Now, from my North Pole, I'm going to take a vector that goes down. Okay, so you imagine you've got your North Pole and you're traveling south. Okay, and the arrow is always pointing in the direction you're going. So you end up pointing south there. Okay, so there's
not too clear. Can you just? I can't see it.
Okay, I've got a better. Here is what it looks like on a nice polystyrene ball. Okay, yeah. I started my arrow here. Okay, and I've gone south to the equator. Okay, yes. So London is about there. Let's pretend I've gone to the equator. Okay, which I know somewhere in the Atlantic, is it? Yep. And then I go round. Okay, but I keep pointing south. Okay, because I'm parallelly transporting it. Okay, so I'm going round until I get to this point here. I then go back to the North Pole. Okay, so hopefully some of you at least have managed to draw that on your orange. Oranges are better than apples because they're a bit more spherical. Although I'm sure some of these managed to buy an orange or using a Satsuma or something that's not round. Okay, the point being, the arrow is pointing in a different direction. Okay, can everybody see that? Right, so what's happened here? This is curved. Okay, and we've measured the curvature by transporting an arrow round. Okay, and it pointing in a different direction. Now, this is going to really, I'm really not sure this is going to work. Okay, but you can do the same thing with the inside of a torus. Okay, so you can see that there. Okay, I'm not really expecting anyone to quite manage that yet. The point is, when you're on the inside of a torus, what is a straight line? Okay, well, clearly, I've got some examples here. So this here is a straight line. That's going all the way around there. The black line in the center, okay, of my torus, that's also a straight line. They're easy ones. There's sort of degree of symmetry telling you what's going on there. But what about if I start off in that direction? Well, in this direction, I curve away towards and then away. Okay, so the concept of straight line is a bit difficult to see when you're on the inside of a torus. Okay, but you can, if you cut open your bagel. Okay, and this is obviously being recorded, so you might want to do this later. You can, so let's say we start at A here, okay, at the top, and I parallelly transport it round down to B. Okay, so they're all pointing round the bagel, so they're definitely doing that. Okay, I then travel along this curve here, so they're all pointing that way. All right, there you go. They're all pointing that way. I then parallelly transport it back to here, but now the important one is as I go from here to here, because this is a straight line, or geodesic as we call it, my arrow is always pointing in the direction I'm going. The angle doesn't change. Okay, so whoopsie. So as I go from D to A, my arrow points, and you see there's an angle here between the angle that I started on and the angle on I've finished on. Okay, I should point out that when we do send out the Einstein packs, these will be drawn by undergraduate minions. Okay, we're going to employ a whole bunch of undergraduates to draw all these lines. Okay, but the teachers can then get a load of bagels and try it out on that. Okay, so we've got the sphere, which I've now lost. Can anyone see the sphere? Here it is. Okay, that has positive curvature, and we have the inside of our bagel, which has negative curvature. Now, has anyone managed to draw either of these lines? At least, well, hopefully most of you can do this one. Has anyone managed to do that one? It did require a lot of thought, so good luck with that.
I couldn't do it. I've ended up with a triangle.
Very good.
I didn't know where to go after that.
Okay. Yes. Now I appreciate this is quite a complicated one. The easy one then is this concept here. I'm going back to the slide here. This concept of geodesic deviation. Okay. Now, the idea being a geodesic, well, in geometry, a geodesic is a straight line. It's the shortest distance between 2 points. Yes, it is. In space-time geometry, if a particle is not undergoing any forces other than gravity, which isn't a force, so it's not undergoing any forces, it will travel on a geodesic. And as we saw here, geodesics either move together or apart. Okay, well, we can see that now in my Einstein ball. Okay, so we start off and we draw on your piece of fruit. Okay, you want to draw 2 geodesics. Okay, make one of them, well, they're both equators. Okay, they are going to look something like that. Okay, and that. It's easier with an orange. Just think about orange segments. Okay, draw lines from the north, the pip at the top to the pip at the bottom, or whatever there is at the bottom, and draw 2 segments. Okay, and now try and consider what the one colored segment, one line is, what it looks like to the other line. Remember, if I go back to here, what matters is what's the relative acceleration due to of these geodesics due to the center of the lift. Okay, so we look at this case here. Okay, and we imagine that we are the black line and we're looking at the blue line. Okay, so here's the black line, here's the blue line, and I'm looking at it, and what I see is it starts off moving away from me. Well, that's like an initial velocity. Okay, if something starts off moving away from you, at this point here, they are moving in parallel. Okay, and then it's moving towards me. Okay, so it's as though there is an artificial force pushing the blue line towards the black line. Okay, so that's equivalent to this artificial force here pushing these 2 dots together. Okay, so there's a positive curvature bringing those 2 together. Okay, so does everyone see that positive curvature is leading to this 2 things, these 2 lines coming together like that? Well, this one, fortunately, is a lot easier to do on your inside of your bagel. I hope you've got a bit of bagel left. Okay, so now we take our lines, and we've got our black line here. That's the observer, and we've got these red lines here. And now, if I'm the black line looking at the red lines, they start off moving towards me and end up moving away from me. Okay, so it's as though there's a force pushing these particles away. Okay, so that's a negative curvature. So we've got positive curvature in our ball, we've got negative curvature in the inside of our torus. Okay, we've got here.
Jonathan,
Yes.
I can see what you're doing here, but what I can't work out is what, well, you know, I can draw that line. You know, I've got my first line, which is my geodesic going a straight line.
Yeah.
And then I can draw a curve above it to show exactly what you're wanting to do, which I've done there.
Yep.
So, but how? What I don't get is how. You know, what's the physics behind drawing that line apart from making it the shape that I want it to be?
Well, the both lines you've drawn are geodesics. Now, it's not obvious that a geodesic on the inside of a torus looks like this red line. Okay, you have to take that on trust or solve the differential equations associated with it.
Right. Okay. Right.
Okay.
Yeah.
But I'm pretty sure it is. To be honest, I've not solved the differential equations associated with it. And it's not obvious to me how any intuitive way of seeing it. Okay, I guess what you should do is you should make a perspex torus, and then what you would be able to do is take, you know, a piece of string and pull it tight and check that that's what's going on.
I see. Okay.
Phil, can I come in and ask a question there?
Of course you can.
Just to see if I can get my head straight around this. So, Jonathan, are you saying that if you were, say, a little insect walking along the black line, you would see the red line approaching you and then moving away from you?
That's right. So if there were two insects, one on the black line and one on the red line, and they were both moving in what they thought was moving in the shortest distance, where they're both on geodesics, you would see the other insect moving towards you and then moving away from you.
And then moving away from you.
So you'd think that there was a force on that insect pushing that other insect away from you.
Okay, I see that. So is the point of this then basically saying that the motions of things that we see on an everyday basis are in fact because space-time is curved in this way?
For gravity, yes. Of course, most of
Right.
what we see are effects of electromagnetism and other forces. Okay, when I pick this pen up, okay, when I drop it, it's gravity, but everything else, the fact that this pen stays pen-shaped, is all to do with electromagnetism.
Yes. Okay, thank you.
Okay, so just to summarize, you know, I call this my gravity ball and I call this my gravity donut. Okay, why? Because as we saw on the ball, it forced things together. Okay, geodesics, even though these were all falling independently of each other, when observed from the center, they were observed to come in together. And these two objects here, when observed from the center, are there's a pseudo force pulling them apart. Well, we've got objects coming together, objects going apart. All you have to do is weave these together into some complicated four-dimensional object, and you've got gravity. Okay, so that ends my demonstration. I hope you found that helpful, and thank you very much. Any questions? Any more questions, I should say.
That's great. Yeah, come on, let's see if anybody would like to have a discussion with Jonathan about this. So just put your cameras on and talk away. Looks like you're bamboozled. Oh yeah, we've got something. Right, great. Is it? Fire away. You need to be unmute yourself. Thank you.
I don't have any questions. Just really enjoyed it.
Oh, thank you.
Just trying to get my head around it.
Don't go away because we got the plenary coming up. Thank you. That was nice. Well, Jonathan, it looks like you have bamboozled us all into silence. Thank you so much. Obviously, these ideas, as I said at the beginning, you've been working on them for a long time. And hopefully, you know, it's a teacher's job to take it into the classroom and make them accessible to those people who are interested. So I'd like to thank Jonathan for his talk. What I've been doing here is asking you to put clap, clap, clap in the chat, because Jonathan will see all the claps and I will clap. And those people, I mean, give Jonathan a nice round of applause, please.
Thank you very much. Thank you.
The claps are coming in.
I hope you can take some of those ideas and possibly even some of the questions to your A-level students.
Well, I think it's going to take a bit of time for us to get our head around, Jonathan. I think we need to revisit it with you some time in the future. So, so I think maybe in a few weeks' time, we'll come back to you if you don't mind, and have another session on this.
Okay.
Right. Okay. And somebody said we'd love some further reading advice, Jonathan. Have you got something? I know there's a book by I've just got it in my bookcase here that I've got. I thought which was quite good. Just come on there.
I mean, to be honest, I don't know. You know, I know a lot of really complicated and heavy mathematical textbooks on gravitation, which wouldn't be appropriate, and I know lots of popular science books, but the popular, well, I don't know a lot of them. I know a few of them, but they don't really emphasize, as far as I can tell, this sort of geometric aspect. It may be in there, but it tends to be sort of downplayed, often in favor of some quite boring calculations, the sort of A-level calculations of working out gamma factors and stuff. Yeah, I don't know if there's good reading. Let's see what Phil comes up with. What are the textbooks that the teachers have at the moment for their A-level physics?
Stephen Hawking's Universe in a Nutshell. It's not very clear, is it? Can you see that?
I mean, I know that book, yes.
It's got some nice pictures in it. I bought it because it looked as though I might be able to follow the pictures. I'll put that in the chat. Right, okay, Jonathan, you're off the hook.
Thank you. Thank you.
I shall do my plenary with our. Can you? I'm going to stop you from being presenter. Thank you very much again for your time. And I'm going to take over being presenter.